Understanding hard and soft acids and bases. This presentation explores the concepts of hard and soft acids and bases, their characteristics, and their applications in chemistry. Definitions of hard and soft acids and bases. Hard acids. Small, highly charged cations with a high positive charge density. Soft acids. Large, polarizable cations with a low positive charge density. Hard bases. Small, highly electronegative anions with a high electron density. Soft bases. Large, polarizable anions with a low electron density. Characteristics of hard and soft acids and bases. Hard acids form strong bonds with hard bases. Soft acids form strong bonds with soft bases. Hard bases prefer to donate electrons to hard acids. Soft bases prefer to donate electrons to soft acids. Factors affecting hardness and softness. Size. Smaller ions tend to be harder. Charge. Higher charges lead to greater hardness. Polarizability. Greater polarizability indicates softness. Interactions between hard and soft acids and bases. Hard acids prefer to interact with hard bases. Soft acids prefer to interact with soft bases. Hard-soft interactions are generally weaker. Applications of hard and soft acid-base principles. Inorganic chemistry. Predicting the stability of complexes. Organic chemistry. Understanding the reactivity of organic compounds. Biochemistry. Explaining the binding of metal ions to biomolecules. Limitations and exceptions to the theory. Intermediate cases. Some species exhibit both hard and soft characteristics. Environmental factors, solvent effects and other factors can influence interactions. Complex systems. Predicting reactivity in complex systems can be challenging. Conclusion. The hard-soft acid-base principle provides a valuable framework for understanding chemical interactions. Despite limitations, it remains a powerful tool in various fields of chemistry. Magnetic and optical properties of coordination compounds. Coordination compounds, also known as complex compounds, play a vital role in various fields, including chemistry, biology, and materials science. They exhibit fascinating magnetic and optical properties that are directly linked to their electronic structure and the nature of their ligands. Introduction to coordination compounds. Central metal ion. A coordination compound consists of a central metal ion surrounded by ligands, which are molecules or ions that donate electron pairs to the metal. Ligands. Ligands coordinate to the metal ion through a coordinate covalent bond, forming a complex ion. The number of ligands attached to a metal ion is known as the coordination number. Crystal field theory, splitting of d orbitals. Ligand field. D orbital splitting. The interaction between the metal d orbitals and the ligand's electron pairs causes the degeneracy of the d orbitals to be lifted, resulting in a splitting of the d orbitals into higher and lower energy levels. Crystal field stabilization energy. The energy difference between the split d orbitals is known as the crystal field stabilization energy, CFSE, which plays a crucial role in determining the stability and properties of the complex. Magnetic properties, spin and orbital angular momentum, spin angular momentum. The magnetic properties of coordination compounds arise from the spin and orbital angular momentum of the unpaired electrons in the metal ions d orbitals. Orbital angular momentum. The orbital angular momentum contributes to the magnetic moment of the complex, but it is often quenched in octahedral complexes due to the symmetry of the environment. Magnetic moment. The overall magnetic moment of a coordination compound is determined by the sum of the spin and orbital angular momentum contributions. Magnetic properties, high spin versus low spin complexes. High spin complexes. In high spin complexes, electrons occupy the d orbital singly before pairing up, resulting in a higher magnetic moment. Low-spin complexes. In low-spin complexes, electrons pair up in the lower energy d orbitals before occupying the higher energy d orbitals, resulting in a lower magnetic moment. Optical properties, electronic transitions in coordination compounds. Excitation. When a coordination compound absorbs light, an electron in a lower energy d orbital is excited to a higher energy d orbital. Transition. The energy difference between the two d orbitals corresponds to the energy of the absorbed light, determining the color of the complex. Color. Complexes absorb certain wavelengths of light, transmitting the complementary colors, which are the colors we perceive. Color in coordination compounds. Ligand field strength. The strength of the ligand field influences the energy difference between the d orbitals and, consequently, the color of the complex. Metal ion. The nature of the central metal ion also plays a role in determining the color, as different metals have different electronic configurations. Coordination number. The coordination number, which is the number of ligands attached to the metal ion, can also influence the color of the complex. Applications of coordination compounds. Catalysis. Coordination compounds are widely used as catalysts in various chemical reactions, including organic synthesis and polymerizations. Medicine. Coordination compounds have found applications in medicine as anti-cancer agents, antibiotics, and diagnostic tools. Materials science. They are used in the development of advanced materials with unique properties, such as semiconductors, pigments, and